Hello, let's talk about section 2.2, which is describing sets. So, in this section, we are going to learn a lot of vocabulary and symbols. It is really important that you understand the symbols and what they mean, because you don't want to confuse things. So, before we start talking about how to describe and work with sets, we need to know what a set is. And a set is a collection of objects defined in a very specific way. A set can be anything from what we commonly refer to as like our set of dishes, a set of CDs, or even a set of tools. But it also can have mathematical references. Now, usually you will see sets done in one of two different styles of notation. There's the roster method, and then there's set builder notation. And it really depends on how many things that you have in the set as to which one of those styles of notation that you use. The roster method lists out each member of a set individually. So this is now we're talking about this roster method here. So for instance, I've given you a set here that says A is equal to the set of 1, 2, 3, 4, and 5. This is a set named A that has as its members the numbers 1, 2, 3, 4, and 5. This is what the notation means. So you can see that a roster method where you list out each method of the set is probably going to be more useful if you have a very limited number of things. Now we also have what we call set builder notation. And set builder notation uses some sort of a rule to list out the members of a set. So, for instance, that same set that we used up here, that A is 1, 2, 3, 4, and 5, can also be written using set builder notation as this. Now, I want you to understand what this means. The brace C means the set of. Then the X is all X's. And now then we have that straight line here. That means such that. And then you have your rule. And your rule here is that 1 is less than or equal to X is less than or equal to 5. So it's really important that you understand. It's kind of like shorthand, mathematical shorthand for the way to write it. So the braces are the set of, then the variable means all x's, the straight line means such that, and then you have your rule. So I hope that you can see that this is going to be much more helpful if you have really big sets. Like, for instance, if you wanted to talk about all of the numbers from, say, 1 to 100, or rather, well, if you said 1 to 100, then, we could write it this similar way. But what if you wanted to say all of the natural numbers? Now, the natural numbers start with 1 and then go to 2, 3, 4, 5, all the way up to infinity, forever and ever and ever. For that, we would say, if we wanted to call this set, say B. B would equal the set of all x's such that, and then we would say x is an element of the natural numbers. Now we'll get into this notation here in just a minute, but that would, because you could see that there is no way we could list out every single number between 1 and infinity. So this is very nice notation when you have a lot of items in your set. And for those of you who've already taken college algebra, you probably used this notation exclusively when you talked about domain of functions. All right, so now let's talk about that little weird E symbol that I put in there. Each member of a set, so back up here in our A equals the set 1, 2, 3, 4, 5, each one of those items, the 1, the 2, the 3, the 4, and the 5, those are called elements. and we use that E symbol to show that something is an element of a set. So for instance, in that set A, we would say that 2 is an element of A. Or we can also use that notation, just change slightly, to mean that something is not a member of a set. So I could also say, like, 15 is not an element of A. So it's really important that you understand that the little e means it's an element. It's not a set, it's an element. It's a member of a set. All right, now talking about sets a little bit more. Two sets are said to be equal if they contain exactly the same elements. It doesn't matter the order, but they have to have the exact same elements in them. So, for instance, if I were to say again that A is the set 1, 2, 3, 4, 5, and B is the set of all x's such that x is an element of the natural numbers. Well, remember the natural numbers go from 1 to infinity, and x, and then the little comma means and. So I should put that in there also. That little comma there means and. X is less than or equal to 5. Well, for both of those situations to be met, we are only talking about the numbers 1, 2, 3, 4, and 5. So these are two different ways of writing the exact same set. They have every single member identical, no more, no less. So we would say these sets are equal because they contain the exact same elements, and we would write it as A equals B. Now, if two sets are not equal, say they don't have the exact same elements, but they have the same number of elements, then we just talk about them as having a one-to-one correspondence, meaning that for every one in set A, there's a one in set B. They don't have to be the same items, but there's the same number of items. So for instance, let's talk about our A again. We're using that same set, 1, 2, 3, 4, 5. And this time B is going to be 6, 7, 8, 9, 10. Now clearly these sets are not equal because they do not have the same elements. But they have a one-to-one correspondence because they have the same number of elements. Now we call sets that have a one-to-one correspondence equivalent sets. So equivalent and equal are two different things. So be very careful about how you use the wordage, because if you mean that the sets are equal, then you're saying that they are the exact same thing. If you're saying that they're equivalent, then that means that they have the same number of items but not the same items. Now our notation for equivalent sets is this. It's A and then a little tilde and then B. So be very, very careful that you don't interchange those words. All right. Now, talking about the number of elements in a set, that's called the set's cardinal number. So, for instance, if we have this set A that has 2, 4, 5, 6, and 8 as its members or elements, the cardinal number of A would be 5 because there are 5 members. Notation for cardinal number looks like this. We would say n, which represents the cardinal number of set A, is equal to 5. It's how many elements there are in the set. Now, you have two different types of sets. There are sets that are finite, and then there are sets that are infinite. A finite set has a specific number of elements. So in other words, you can count the members of the set, or you'd say it has a cardinal number. So for instance, the set 2, 4, 5, 6, 8 is a finite set because it has a cardinal number of 5. You could count those. On the other hand, an infinite set cannot be counted because it goes on forever. So this would be something like saying A is the set of all x's such that x is an element of the rational numbers. That R represents rational numbers. There's no way the rational numbers, remember, are anything that can be written as a fraction. So there is absolutely no way that we could count all of those things. I mean, there's an infinite number of rational numbers just between 1 and 2. So we couldn't count them all. Now, technically, there is a cardinal number for an infinite set, but it's kind of weird. And this is not in your book or anything, this is just a little something extra. Technically, the cardinal number of an infinite set is this symbol, or the name of it is Aleph Null. Now, this little aleph here, and then the null is the zero part. Aleph is the first letter of the Hebrew alphabet. So that's kind of interesting. Maybe you'll see that on Jeopardy or Who Wants to Be a Millionaire one day, and you might win $1 million and be able to thank me in your speech. All right, so let's think about a little bit more about sets here. Think about like everybody has dishes, because everybody has to eat off of something. So think about your dishes at home. You have what you call a set of dishes, but then you can break those down into smaller sets or smaller pieces. Like you could have a set of plates, a set of bowls, a set of salad plates, maybe a set of cups, that would all be part of that bigger original set. These smaller sets are called subsets because they are literally a smaller portion of the larger thing. Now, when we talk about mathematical sets, like for instance, if we had the set A is 1, 2, 3, 4, 5, and if we had a set B that was just 1 and 5, then we would say B is a subset of A. And there are two different notation types for this. So you can see there's a lot of vocabulary, a lot of notation, a lot of symbols in this section to really keep straight. Now these two symbols are very different, so you have to be very careful about which one you use. The first one here, this B and then this little subset symbol and then A, this is called a proper subset. Or another way of putting it would be it's truly a smaller portion of the original. The second one here, with the little line underneath the subset symbol, literally means is a subset or equal to. It's kind of like in our less than, we have less than, or we have less than or equal to. It's the same sort of idea. If you use this notation, the B is a subset or equal to A, then that means the sets could actually be the exact same thing. So, let's say that we have about three sets here. We have A, which is 1, 2, 3, 4, and 5. B is 1 and 5. And C is 5, 4, 3, 2, 1. We would say that B is a proper subset of A because it's truly a smaller portion of the original set. But we could not say that C is a proper subset of A because it's equal to A. So we'd have to use the notation C is a subset or equal to A. That notation is extremely important. Now, I want to talk to you about something that I see all the time, and I understand where it's coming from. Let me get a drink here real quick. Especially whenever you write numbers a lot, like in business and accounting and things like that, you tend to want to make sure that people understand that a zero is a zero and not something else. So I see people all the time write the zero with the slash through it. Now that does not mean zero. That means the empty set. In other words, it's a set with no members. And another way to write it is like this. That set notation with nothing inside of it, blank. So the empty set is not the same thing as zero. Zero is a real number, but the empty set is a set with no members. They have two different meanings. So be careful what you're writing and write what you mean. A lot of times in my classes, even in like when I'm teaching college algebra or beginning algebra or something like that, the I see this notation a lot, and usually the first time that I see it, I'll write a note out to the side that says this is not zero, this is the empty set, and the next time that you use it, I'll count off because it truly means something different. So be very, very careful that you're writing exactly what you mean. It's also important to know that the empty set is a subset of every set. Now, the way it was explained to me, and it made sense to me, which I hope it makes sense to you also, is when I was in college, my instructor pulled out his wallet, and he opened up his wallet where the bills would normally be, and there was nothing in there. He said, "So my wallet right now is empty. There are no members in my wallet. There are no ones, there are no fives, there are no tens, there are no 20s. So every single wallet, whether it has money in it or what, has the potential to have nothing in it, to have no members. So every single set has the opportunity to be completely empty." So I hope that that makes sense. All right, now let's talk about, if you have a set of numbers, how many subsets there are from that original set. So if we had a set with only three elements, 1, 2, and 3, we could list out the subsets pretty easily and pretty quickly. Our first subset would be the empty set because it's a subset of all sets. And then I could have a set that just has 1. I could have a set that just has the number 2. I could have a set that just has the number 3. I could have a set that has 1 and 2, or 1 and 3, or 2 and 3, or I could have the actual original set, 1, 2, and 3. So there are 8 subsets of a set containing 3 elements. Now, if you remember your exponent rules, 8 is 2 cubed. The number of subsets of any set is always 2 to the n power, where n is the number of elements in the set. So therefore, if we happen to have a set with, say we had a set with 8 elements, the number of subsets would be 2 to the 8th power. So there would be a lot more subsets. It'd be a lot harder to write out. And as I was writing this, I forgot about one last thing that I needed to talk to you about, which is a way of visually seeing sets. And that's with what we call a Venn diagram. Now, a Venn diagram is a drawing that kind of puts the sets into picture form. And I wanted to give you an example of what a Venn diagram looked like. Usually, with Venn diagrams, we have a giant box around it, and we call this the universal set, the entire set of items. And then we have circles that represent different subsets of that. So, for instance, we may say, this is the universal set here might be, aquatic um, animals, or I know we probably don't call them animals necessarily, but all of them, but something maybe to that tune. So we have those that can swim and those that breathe air. And so you can see that in here, jellyfish and shrimp, well, those are ones that can swim, but they don't have fins and they don't breathe air, so they're outside of those other two smaller circles. Sea turtles can swim. They all can swim, actually, but sea turtles can swim, but they can breathe air also. They can live out on land. And then you have things like whales that can swim. They're also in the circle that means they have fins. And they're also in the section that they breathe air. They have to come up and, breathe air from time to time. Then you have these that can swim but also have fins but don't breathe air. So those are fish and sharks. And hopefully, we did, by the time that you've watched this video, we have done some practice with some Venn diagrams in an exercise that we did in class. So hopefully now you're ready to work some examples.